Hello, everyone. I'm here to talk about state-of-the-art multimodal inference with Reka on AMD MI300X. But first, let me tell you a little bit about Reka. So I'm going to give you an overview of what we do, who we are, and what our mission is. Reka's mission is to develop next-generation AI to empower the most capable AI agents that can see, hear, and speak. To achieve this mission, we build multimodal large language models. We do this because we think that strong base models with multimodal capabilities are necessary for capable agents. I will tell you a little bit more about multimodality later on. Let me tell you a bit about our team. So we're a pretty young company. We released our first models last year, and our current range of models was released earlier this year. I'll talk a bit more about the models later. But the people in our team, before they joined Reka, have contributed to many important advances in the field. You can see on the slide a lot of large language models, some large multilingual vision language models, many transformers before joining Reka. We're still a small team, like 30 to 40 people, but majority technical, and we aim to punch a little bit above our weight in terms of the quality of the models. So let me tell you about the models. We have a broad range of models. So our smallest model is called Reka Spark. That's a 2.6 billion parameter models, hyper-compact model used for on-device deployment, on mobile, on smart appliances. Next in line, we have Edge. That's our 7B model. It's a light and efficient model that's designed for running on modern desktops or laptops. Our most popular model is Reka Flash. That's a 21B model, perfect size for deployment on premises if you have moderately sized GPUs, and for most day-to-day multimodal activities. Our largest and most powerful model is called Reka Core. That's a 67B, the most capable one for complex multimodal tasks. All of these models have various capabilities, but all are natively multimodal. We also have a range of other models in development, but I won't talk about that today. Okay, so multimodal. I want to talk a bit about where we are compared to other providers on multimodality. So nowadays, all AI providers, or almost all AI providers, have at least some form of image understanding. But if you're looking for things such as video understanding, you find that you have fewer providers. If you want to look at speech input and output, then the list gets even shorter. At Reka, we bet pretty early on multimodal. That gave us a little bit of a head start in terms of supporting a broader range of modalities. Okay, so we say we want models to enable AI agents that can understand and act. So what do we mean by that? If we think about understanding, that starts with image and video comprehension. So we want our models to have visual understanding of images and videos with arbitrary resolutions and arbitrary formats. Given image and video input, the models are capable of generating structured outputs such as JSON or natural language descriptions. In terms of visual capabilities, the models are capable of recognizing objects, understanding spatial relationships. They can understand audio inputs that come with videos, and they can understand timestamps in order to refer to content in videos. So that's for image and video comprehension. The next aspect is multilingual understanding. So multilingual is pretty important if you want to reach as many people as possible. Our models were trained on 32 languages. That allows them to have input and output across several language pairs. Out of these 32 languages, there are 12 core languages where we have the best capabilities. These are languages like English, Spanish, French, of course, and others. So that's for multilingual. Long context is getting more and more important. If you want your models to be able to understand documents, PDF, docs, etc., if you want your model to understand charts, diagrams, tables, and infographics, you need multimodality, but you also need a long context in order to fit all that information. So our models typically support 128,000 tokens. We have options to extend up to 400,000 tokens. We support coupling this large context with retrieval augmented generation, so we can do question answering over private data sets. That's for long context. Now, speech input and outputs. That's pretty important. We have end-to-end speech input and outputs. So that's different from a pipeline approach, where you first do speech recognition, feed the text into an LLM, and then do text-to-speech. We have the ability to do end-to-end speech input and output. that results in richer capabilities and lower latency compared to pipeline. So that's for understanding, but there's also action. We want our models to be able to take action to enable agentic workflows. So for that, we have code execution, tool use, and function calling. So that allows us to build agentic solution with top-tier code abilities and function calling. We recently released an update to our model, improving our function calling results. I can talk a little bit about the capabilities of the model on standard benchmarks. So this is an evaluation of our model compared to a range of other models on standardized benchmark. I won't go through all of them, but we can talk maybe about MMLU, which evaluates general text understanding capabilities. And you can see that our Flash 21B gets a score of 76, which is very competitive for its size. We can also highlight BFCL v2, which is a benchmark that measures the capability of models to use tool and to do function calls. And here, Reka Flash gets 80, which is close to state of the art. So the models are pretty competitive, in particular with their size. Okay, so we have good models, but we also do things a little bit differently in terms of how we deploy them. We're pretty flexible on how we deploy them and how we work with our partners in order to deploy. So how we deploy? We have a range of options. The simplest one is maybe our hosted API. So that's where the model is running on our Kubernetes cluster. We're doing the inference, and the customer accesses it via the API. Or maybe we're running it on another cloud service provider, and we charge by usage. But we also do on-device. So that's where the smallest models are built to run natively on-device, and then we bill the partner via a licensing fee. Finally, we have on-premises. So that's where we deliver the model to the customer who runs them on their own hardware and are also billed via a licensing fee. In terms of how we work with partners, we also have a broad range of options. The most basic one is where our partner just takes one of our standard models, customize it if they want, but they do the work on their side, and deploy it themselves. In that scenario, they rely on Reka only for updates. So when we improve our models later on, maybe we provide them with updated weights, improve the ability on some of the benchmark or some of the performance. We also have options where the partner chooses a base model, but then provides us with some data. This can be a one-off. They provide us one data set, and we customize the model for them. Or this can be on an ongoing basis, where we get regularly data feeding in, and we improve the model with time. Then we could, for example, host the model ourselves and deliver it via API. The last option is where we do the customization, but this time we also provide the model weight to the partner. We find that that's pretty important for some people who like to have full ownership of the weight and be able to do their own deployments. In that case, the model is also provided via a license. Okay, so I've talked a little bit about the model. Let me talk a bit about multimodal capabilities. I want to talk about why it's exciting, and I think one way to convey why it's exciting is to show you a quick video that we made a few months ago about multimodality. So this is a video that shows you how it would be like to watch a TV show with an AI assistant next to you.
There must be 30 dead scientists in the past month. Christ, another countdown.
Has anyone else seen it? What happened to them?
Someone or something is targeting scientists.
They're gone after our best and brightest. There's someone behind everything. You just have to dig.
Whatever it is, it's watching and listening.
Okay. Thank you. One of our engineers made that video, actually. Okay, so I talk about state-of-the-art multimodal models, but if we claim state-of-the-art, then we need careful evaluation. So I want to talk a bit about an evaluation dataset and framework that we have designed. We call it VibeEval. So VibeEval is an open benchmark and framework for evaluating multimodal chat models. It's open in the sense that you can use it, and we know of other AI providers who actually use it in production. It consists of 260 visual understanding prompts, including 100 that are very hard, selected adversarially, so we pick them in order, we pick the hardest one that the model couldn't solve. And we include gold standard responses authored by experts. Some of the questions will take general knowledge, such as the one you see here, where we ask about some pictorial scripts. Some of the questions are more oriented towards some basic reasoning, such as the ones about the scissors. All of them can be evaluated via AI as a judge. So you let the model generate an answer, and then you feed that to a different model who evaluates the quality of the answer. We, of course, verified with human raters that the evaluation from the AI model actually correlates well with human evaluation. So why did we create this benchmark? We created this benchmark because external benchmarks are not always sufficient. We found a few issues with external benchmarks. One of them can be test set contamination. So if your model is trained on a lot of data pulled from the internet, and if your benchmark also uses data from the internet, then you can have a bit of contamination. The model may have seen the data already. There are also issues with oversaturation. So that's where the benchmark is already too easy for the current generation of models and doesn't allow you to distinguish between different model qualities. One other problem that you can have with external benchmark is overspecialization. So that's where a benchmark targets a very specific range of capabilities, but doesn't measure the broad range of capabilities that you want your model to have. So that's why we created VibeEval. So to tell you the history of VibeEval, like most AI people, we have our own range of prompts that we keep secret and that we typically give to new models that come out in order to evaluate and understand how good the models are. We decided to just take this and formalize it into an eval, and that's why we called it VibeEval. So we tried to put the difficulty of the benchmark in this Goldilocks zone. So you want your benchmark to be not, as I said, oversaturated, because then all your models are scoring 100% and you cannot distinguish or measure progress. But you also don't want your benchmark to be too difficult such that all the models fail and you also cannot distinguish. And we think VibeEval strikes the right trade-off on that dimension. It's designed to be hard enough not to be saturated, but easy enough to measure incremental progress and to rank models. In fact, we can look at model rankings. So this is a ranking that we did a few months ago where we evaluate a range of multimodal models. This one is testing only image understanding on VibeEval. The first column is the general score, so that's the score across both normal and hard prompts. That's what we use to rank. And then the next two columns are the hardest prompts, so the ones that we picked adversarially, so the ones that are hard for the models, and the normal ones. As I mentioned, we picked the hard category adversarially, so that means that our model is not doing as well as it could be doing on that category because we picked the prompts so that our model does poorly on them. Okay, so that was about the model. Hopefully I've convinced you that we have some good models and that they are close to state of the art. Now let me talk a bit about how we serve them, and in particular how we serve them on AMD, since that's partly why I'm here. As I said, we have a range of deployment options. We deploy on our own Kubernetes cluster, we deploy on premises for customers, and we deploy on various cloud service providers. We also have a broad range of hardware. We deploy on mobile devices, we deploy on mid-sized GPUs, and we deploy on largest GPU clusters. So that poses a few constraints on our inference stack, but there are more constraints. We have a broad range of model sizes, we have different context lengths. We have different workload shapes, so some customers just want to run chat evaluation, or they want a chat model, so they're talking to the model is answering, but that's typically small amount of requests going in and out. Some customers want to run batch workloads, so they have a large set of images, video, audios, and they want to get structured data out of it, and then they care a lot more about throughput than about latency. If you try to take the Cartesian products of all the model sizes, all the context lengths, the workload shapes, and the possible deployments, you get a lot of possible options. So quantization is also very important for us because that's one degree of freedom that you can use in order to make all these combinations work. In terms of software stack, so we build on top of a lot of very good open source tools. So for the front end is Fast API. The back end is built on top of a fork of VLLM. So we forked it in order to support multimodal and to add a few improvements. And PyTorch is used to define the model architectures in order to have enough flexibility. Now I want to talk a bit about how it was working with MI300X. So that part of the talk is more developer-oriented, You can think of it more as a return of experience, how it went for us porting our stack to MI300. So our experience is still pretty early on. We have our models running, but we haven't spent that much time on it. But I still want to talk about it because it was a bit different from what we expected. So for example, we have hundreds of lines of kernels. Some we wrote ourselves, some we took from open source projects. But that's a lot of kernels. And yeah, that's only a small subset of our kernel is already thousands of lines. So we were a bit thinking, okay, how much effort is it going to be if we need to port all of that to target a different architecture? In the end, that concern was completely unfounded. It barely took us a few days to port all our inference stack. It's not a matter of weeks, it's a matter of days. The reason for that is that many standard libraries and frameworks are already ported. So VLLM, you're going to hear more about it later. TGI from Hugging Face, we're not using that, but I think it's already available. Flash Attention, of course, Xformers, etc. So having all these acceleration libraries already available and running on AMD GPUs was very helpful. Another reason that we were able to get things up and running quickly is that the heap ecosystem is pretty mature, well documented, and generally nicely designed. So in particular, one thing that I found nice personally is that heapcc is open. So the compiler is open and based on LLVM. So that means you can get the latest patches directly. This happens like very concretely to us. Like we were trying to heapify some kernels and we had a compiler error. So probably we could have worked around it or we could have changed things in our kernel, but that's a bit of work. And it requires some testing, etc. But it turned out that this has already been fixed upstream in the latest version of LLVM that AMD uses. So instead of having to wait for a new release of the compiler or to wait for our CSP to roll out new images, etc., we could just take the patch and apply it directly. So this is a small thing. Maybe there is a way to fix it, but all of these small things can make for a nicer developer experience. Having the compiler open makes for a nicer developer experience. That's one of the benefits. Okay, so we talked about porting the stack. So as I said, that went reasonably well, but then there were some questions about performance tuning. So the kernels that we have were mostly optimized for different hardware. So we were wondering, okay, how competitive is performance going to be out of the box? We also know that GPUs can have pretty steep learning curves and a lot of documentation to go through. So how much time is it going to take us to tune performance? In particular, our GPU engineers, they're very good, but they're very good at optimizing workloads, but they're not necessarily that familiar with AMD or ROCm. So how hard is it going to be for them to tune the performance? So if I think about my own experience, I'm not a GPU expert. So in my career, I started, with small amount of GPUs. Then I worked at Google, where I was mostly training on TPUs. And then at Reka, we use a lot of GPUs. We use enough GPUs that we can train these powerful models, but we don't have that many GPUs that we can afford not to care too much about performance. So we do need to do this performance tuning. In this project, we were mostly focused on the lowest hanging fruit. We just wanted to see, okay, how far can we go with some small amount of time. We were lucky enough to have some good help from AMD, but the documentation for ROCm is also pretty good. You have step-by-step guides on performance tuning. So the first thing we did, the easiest one, is to just enable PyTorch tunable ops. So if you're not familiar, that's just a way from PyTorch to select the best linear algebra backend for each of your gem size and floating point types. And just, okay, I'm putting one line of code. It's a little bit more work, but it's not that much more work than one line of code. And already that gives you like plus 6% throughput and minus 5% latency. If you think about it, plus 5% is quite a lot for frameworks that are already pretty optimized on these GPUs that are quite powerful. I'm giving figures here for MI300 out of the box and after optimizing with just tunable ops. And yeah, as I said, we have reasonable improvements. There are some caveats about how you do performance tuning with tunable ops, and we're still working on going a bit further than that to get the best performance, but we are already able to get competitive performance for inference. Okay, so these are the same results in image form because multimodality is cool. But yeah, you can see that total throughput gets better after these tunable ops, latency decreases. Okay, so the overall message I want to get across is that running multimodal inference on MI300X with competitive performance is easy, and that's thanks to a mature ecosystem. So what I mean by mature ecosystem, I mean that these acceleration libraries, which are already available out of the box and that run directly on the GPU. We have some high-quality documentation and some good guides for performance tuning. We have an open and robust compiler toolchain and accessible performance tuning. So all of this enabled us to get competitive performance on MI300X, but we also had some help from AMD, so I want to give some thanks and credits to the Reka team, so in particular Kaloyan for helping us port our stack to ROCm, to Reka for training good models. At AMD, I want to thank George for performance tuning. I want to thank Karim for incredible support. And I also want to thank VLLM, PyTorch, XFormers, Flash, and ROCm contributors. That's all the stacks that we're building on top of in order to be able to serve our models. That's it for me. Thank you.